Hey, how are you doing? And what did you eat?
Um, yeah, so I have the practice test and I started going over it. I went over like all of the chem phys so far, but I had like a couple I just like had no clue on and one
Mm-hmm.
passage. So I'll share my screen.
Uh, yeah, here. I'm looking at one of the questions you sent me, but I can do that after.
Oh yeah. I didn't know how to derive those
Mm-hmm.
the third or I don't even remember which one it is now.
Mm-hmm.
Hold on, Safari. Okay. Number six. Okay, yeah, this passage I like had no clue how to do. I ran out of time on it, but I also like came back to it when I went over it,
Mm-hmm.
and I still had like no clue.
Mm-hmm. How are you doing? Are you still sick?
Yeah, I'm like okay, I just had like a little cough still, but
Was it like a sore throat? Strep?
yeah.
Strep?
Better though. How's your girlfriend?
Oh, she's good. Um, Thank you for asking. Let's see. Oh, cool. That sounds interesting, at least to me. But let's see.
Yeah,
The
not to me.
the Voigt model, asymptotic limit. I also like that kind of stuff. Okay, so base. All right. Let me see. So, Voigt model, Maxwell model. Okay, Voigt model. Okay.
Yeah, like I
Yeah.
honestly had no clue what this whole stuff was like saying.
Okay. All right. So let's see. Certain biological materials like human cartilage have a unique property of viscoelasticity. Viscoelastic material has both the. So wait. First of all, visco. What does that sound like to you?
Is that a viscosity?
Yeah. Which is like what in your words,
Uh,
or what comes to mind?
I want to, I know it's something about liquids. I just can't tell you what it is.
So
Like how,
what?
it's something about the flow.
Mm-hmm.
I don't know.
Let's say
Liquid.
what what about honey?
Okay, yeah. It's like is it the resistance to flow
Mm-hmm. Yeah.
or, okay,
So honey is viscous.
okay.
So yeah. Okay. So viscoelasticity is going to be combining those things. Um,
So it's the resistance to being like compressed. Is that what
um,
it is?
so okay. First, the viscous part, right? Honey, right? It's not really like completely a fluid, not really completely a solid. It has properties of both, right?
Yes.
So something that's viscous is going to be like that. It's going to have properties of solids and liquids, just like honey.
Okay.
Because honey isn't, right? It's like not really
Yeah,
completely.
yeah. It's like thicker. Yeah, so solid and liquid. Okay.
Got it. So that's the characteristics of the solid and fluid part, right? So they're
Hmm.
saying that it's going to be analyzed using separating the components, the solid and fluid components. Um, and then the elasticity part, um, elastic, something like. So what's elastic to you?
Um, like something that stretches.
Yeah. So like we think of it generally as something that can stretch. In physics terms, it's more we're focused more on the ability for it to return to its original state after being stretched.
Okay.
So like, yeah, like generally speaking, like when we think of, clothing or something that's elastic, we think it has the ability to stretch, but everything has the ability to stretch. Something that's elastic simply has the ability to go back to its original state after being stretched.
Got it.
All right, so let's see. So the solid component of the material is modeled as a spring where the elastic force of the material exerts to resist deformation is proportional to the degree of strain. Okay.
Yeah, that's where it lost me.
Yeah. So, oh yeah, let me get my tablet. So there's a difference between, when we're dealing with elastic properties and things like that, we look at two things. We look at stress and we look at strain. Now, stress is what you place upon something. Like if you had, like this, like, right here, like that.
Oh.
So, okay. So this, this is like it, like normal. Sorry, like this is like it normal. So stress is what I apply to it. So I can pull it, right? That's the stress that I'm applying to it. The strain is what is happening to the material itself. It's like if the MCAT is giving you stress, the effect on you is is strain.
Okay, so the stress is like what you're applying, and then the strain's the effect.
Yes.
Got it.
Okay. So yes. So that's where they define the elastic force as a material is something that the material exerts to resist deformation, aka the stress, right? And that is proportional to the degree of strain. And then they talk about Hooke's law.
Solid component of the elastic force of the material exerts to resist. So it's saying the solid component of the material is modeled as a spring, so the elastic force. What is the elastic force?
Oh, yeah. So the elastic force is the thing that resists that deformation. So, like, for something to, like, stretch, the elastic part of it is what resists that stretch and helps it go back to its initial state.
Okay. So.
Okay. So, and then they say it's proportional, right?
Yeah.
So okay, tell me what that means.
It's proportional to the degree of strain. So is it just saying like the higher the elastic force, the lower the strain?
Well, it's proportional rather than inversely proportional, right?
Oh, so the higher the elastic force, the higher the strain?
Yeah. Yeah, they're proportional. And like if you think about it, like think like the more strain you put
Yeah, that
on
makes
it,
sense.
the more it'll have to use elastic force to return it back to normal.
Got it.
Okay, now, so essentially F is proportional to, oh wait, X is the, wait, let's see. X, yeah, amount of elongation, K is the stiffness, elasticity. Okay. So, all right, then they talk about the fluid component. Oh, sorry.
Wait.
Yeah.
So Hooke's law, the F is the elastic force, so that's what is resisting the stress. And then the K is
You could think of it as like a restoring force, but I'm reluctant to use the word force because force has a very specific,
yeah,
like thing in physics. But yeah, you could think of it as it's the restoring. Yeah, sure, you could think of it as the restoring force.
Okay.
I kind of go into this in one of the cards, Anki cards. Let's see if I can find it. Because I explain like basically, or I go over like the theoretic, like the conceptual idea of this, of restoring forces and things like that. Also in like one of the OneNote pages, I talk about it. I think in the formulas.
Open my OneNote.
I'm going through the. Oh, I should just go by like search or whatever. Whoops. Okay. Let me just.
I'm in like the formulas section. I do not see it, but I also could definitely be missing it.
Let me see.
I just see like the linear rotational. I mean, maybe this is it though. Can I add it?
Oh yeah, I guess I didn't. Oh, so I didn't like write it out, but so yeah, the. Okay. Let me just go to my Anki. Let's see. Check. No, check media. Wait. Oh yeah, sorry. I have to go to browse. Okay. Got it. Okay. All right. So in one of my Anki cards, I talk about simple harmonic motion. And I wonder if I could, in the chat, send... Yes, I could send. So, here.
I think I've got to stop sharing my screen to look at that.
No, I think I could send a,
Wait, where did my Safari go? Oh, okay.
Here, I'm going to send it in the chat.
Okay.
Okay, I sent it.
Got it.
All right. So yeah, show it on your screen so I can like go over it.
Oh, yeah, let me see if I can like just share my...
Are you using like multiple screens or whatever?
I have no idea. Can you see everything now?
Yes.
Okay.
Okay, so this is the case for simple harmonic motion, but spring is an example of it. So conceptually, there must be, after a disturbance, a restoring force and a value that causes it to overshoot. So basically, that elasticity, that's the restoring force that tries to... so in Hooke's law, the X part, that is, causing a disturbance to it. right? A stretch.
Yeah.
And
The x is just the distance, no?
the distance that you stretch it away from equilibrium, which in the purposes of this passage, you can just think of it as strain.
Okay.
Right?
Yes.
And the elasticity, the K thing, is a restoring force that tries to bring it back to equilibrium.
Okay. So then, got it.
Mm-hmm. Yeah. Let me show you another thing. Stress versus strain. Curve. All right, you know what? I'll show it later. All right, all right, so let's see. So, okay, Hooke's law. So that's how they model the solid component. Okay?
Okay.
Side tangent. When we look at, like, in quantum mechanics, like, this isn't on the MCAT, but we basically, to learn about, like, the nucleus and the electron that, is like basically kind of like we model that also as this type of thing, as like a spring.
Okay.
Like yeah, we call it particle in a box or harmonic oscillator. So okay, so they're using the solid component of this viscoelastic material, right?
Yeah.
They model that by treating it like a spring, right?
Yeah.
Okay. Now, the fluid component of it, they model it as something called a damper. Now, what's
Yeah.
yeah.
Am I supposed to know what that is?
Oh no.
Okay.
They're going to tell you right here. So, this is just essentially what you need to know is just that the viscous force is proportional to the speed of deformation. So v is the speed of elongation, which is deformation, right?
The speed of elongation. Oh, you're saying elongation is the deformation?
Yeah.
Deformation?
Mm-hmm.
Okay.
Yes. And then that symbol, I forgot what it was called.
I have no idea. The N?
Yeah.
Okay. Yeah, I have no idea what it's called.
Yeah, it's weird because they also use that for viscosity, but in this case they're using it for strain, it seems.
Okay. So.
Oh, it's a lot.
Yeah, I have no
Eta.
idea. What's it called?
Eta.
Oh, yeah, I didn't even know that ever.
Okay, so eta is the dampening effect or Oh yeah, it is viscosity. Yeah, because in physics we use that for viscosity. All right, so the elastic force will increase with more strain, and the viscous force will increase the faster the material is strained.
So V is like how fast it's getting deformed?
Mm-hmm.
Okay.
Yeah, so I would just write like force of like whatever.
Yeah, like what am I supposed to be writing when I read this? Because like I have so many notes now.
So like when I write the proportionality, like it looks like a Jesus fish, like, so I would write like force of the spring is proportional to the degree of strain. So I guess like since they don't tell you exactly, but the degree of strain, we think of that as the amount of elongation, so proportional to x. And then the force of, I'll just write like damper, is proportional to basically the I mean, it's going to be proportional to either, but they are saying speed, so I'm gonna write down like V.
Okay.
All right, now let's see. So hence the elastic force will increase with more strain, and the viscous force will increase the faster the material is strained. Using these basic principles, two models have been proposed for the analysis of viscoelastic materials. Okay. So we have this Maxwell model, and yeah, you can. All right. So this is so viscoelastic materials should be analyzed with the viscous and okay, I get it. So this is just a model that puts it in series, and then the Voigt one is in parallel, and if it's in series, like connected, kind of like a resistors in series, right? In a straight
Yeah, like
line.
there's only one
one path
for it.
Exactly.
Right.
Yeah. So in that model, the stress provided by each form is the same, and the elongation of the material under under constant stress is, so this is like I guess like
Yeah, I have like no idea what this is showing me here.
Oh, so this is
Like I
just
see they're in series, the K and the N, but so the K we said is like
yeah.
I have no idea.
So this isn't actually what it looks like physically. This is just a model representation. So like the K is just all you need to know here is just that if we treat them in series, we're going to get the type of result that you have in that graph over there.
Okay.
Yeah.
Oh yeah.
So tell me what's happening in that graph, like.
So the elongation, the stress provided. So if there's constant stress, I guess elongation. So does it just start at a certain distance, and then as the stress is applied, it's
so
elongated?
Yeah. So we're looking at the two different. So we're looking at the two different components, right? So the elongation part, right? That is the solid, like the solid portion of it. Here, I think I'll do this. I'll screenshot that. I'll put it in whiteboard, and then you can see what I'm writing in real time.
Oh, so should I unshare? Or no, not yet. Sorry.
Yeah, one sec, because I want to get the other half of that as well. All right, you can scroll down to the other part. Okay. Oh, let me get the
top.
Yeah, also, because I'm gonna like also like just copy this into your notebook. So okay. All right. So.
Good.
Yep. Let me go to it here.
So should I open?
All right.
Is it in just the Kaplan? Are you gonna put it in that? Oh, you're trying. Okay.
Yeah, I'm gonna like put it in whiteboard first because it's just the fastest, and then Perfect. I'll put it in your OneNote here.
Okay.
All right. So basically, Um, okay, so let's see. I'll write some stuff down. So I'm just gonna write VE for viscoelasticity. Means that, you know, it's going to kind of behave like a solid and, well, fluid. And the solid component is modeled as a spring. Fluid component modeled as something called a damper. And then the spring is basically governed by Hooke's law here. The damper is governed by...
Yeah, that's way easier.
Mm-hmm.
Okay.
Yes. Okay. Now they're saying he's blue. That X is the elongation, right?
Mm.
Okay. And the and then the other one is speed.
K is the stiffness.
Mm-hmm. So, since they're... Yeah?
So this is X on the y-axis and then V on the X.
Oh, okay. So okay. So the X is elongation, V is speed of elongation, right? So if we had so yes, if we had elongation versus time, right? Sorry, that says elongation.
Hello?
Oh yeah. Do you like
Okay.
hear me or see me?
Yeah, no, now I can.
Okay. So this is elongation on the y-axis, and on the x-axis is time, right?
Mm-hmm.
All right. So if x is elongation, yeah, you'll see that just on that y-axis.
Yeah, and then the V, I put. Oh, so V is not on the x-axis?
Well, which thing?
The V, the speed of the elongation.
So, let me ask
Oh
you,
no,
what would the
like,
speed of
no.
elongation be here?
What would the speed of elongation
Mm-hmm.
be in the graph?
Mm-hmm.
The elongation over time. So the slope.
Got it. Perfect. Good. Good. Excellent. Good work. So yes. Yes. Good. So okay, good. So let's say that something is just going like this, right? Wait, are you able to like see this? Should I like maximize or whatever?
Yeah. That's good.
Okay. So let's say that this over here, right? What's that?
It's just a straight line. Oh, like slope-wise?
Like you know, like what's happening there?
That's, I guess, how like long it is without anything.
All right, here. How about this? What about that?
They're directly proportional.
So
One slope of one.
oh yeah, so like this is basically like the slope isn't changing, so it's a constant speed of elongation. But essentially, yeah, something is getting longer over time, right?
Mm-hmm.
All right. Now, that.
And now it's getting longer over no time.
Yeah, like it just so basically
Like natural state.
so basically its speed of elongation is instantaneous almost. Cuz it basically goes from 0 elongation to some greater than 0 elongation over like essentially like no time. Like no time has passed.
So okay.
Like almost think of well, yeah, elongation is represented as x, right? So think of it in physics terms like almost like, distance,
Okay.
right? And I'm sure you've seen like those like kinematics like or whatever like graphs where it's like a graph of like x versus time,
Yeah.
v versus time, right? Stuff like that. So yeah. So basically, this just means that it got like stretched really, really, really fast, and then let's say like after that point.
As fast.
Say again.
And it like just stop stretching that fast. Slow down a bit.
Yes. Yes, it slowed down a bit and at like a constant v, right?
Yeah.
Okay. Now, not to bring up calculus, but do you remember anything about, like, let's say, I'm just going to draw like two types of things here.
I didn't take calc. I only took pre-calc so far. So.
Did you ever do anything like limits?
No, I don't think so.
Okay, so basically, all you need to know is that. So here, basically, there's in calculus, essentially, not to do another like side tangent, but calculus is basically a way to figure out. So, you're driving in a car, right?
Yeah.
And the speedometer or whatever, odometer, it tells you your speed, right? Now, how does that work? Because, like, isn't average speed like you take, like, I guess the distance that you traveled over time, right? Like, wouldn't that be speed? Like average speed?
Yeah.
So like you would need like to reach your destination to calculate an average speed, right?
Oh yeah, okay.
But on your car or in your car, that speedometer is able to calculate the instantaneous speed without you having to have that end destination.
Got it.
So how that works is there's like you take like a limit essentially. So like let's say I wanted to find like the slope of like at that point or something like that. So you take like a limit of it going backwards to that point. You take a limit of it going forwards to that point, and you see if they're equal. Now, in this case, since there's no curve, they're not equal because I'll use blue. It's seems like this like line going down would continue going down that way, right?
Yeah.
And this one would continue going down that way. So this is an example of what in calculus they say the limit does not exist, and therefore you cannot differentiate it. You can't basically use calculus to find the slope there. Now, for something like here, right? Like if you like zoom in on that, the limits in both directions coincide with the directions that they would naturally go at. So okay, now what's the relevance of this? The relevance of this is that this here, this abrupt change, this like non like curve over here, means that there are two separate actions happening, or two separate events happening. They are not combined. Whereas if it was like this, they're combined. They're basically it's that smooth line, okay?
Okay.
So okay. Now if we go back to so when they do it in series, right? They get this shape over here. And they even say it. Okay. But yeah, they say it. So the two component forces respond independently in two phases of time. So the deformation of the elastic component occurs instantaneously. Which one here, blue or purple? Which one is that describing?
The blue?
Perfect, because it's instantaneous, right?
Mm-hmm.
And then the viscous component is purple, right? Because it responds slowly over time.
Yes.
Okay, so that's that. I'm sorry this is so abstract, but it's making sense, kind of.
Yeah.
All right, so now the Voigt model describes it with the two things in parallel. So, that's just whatever, the schematic drawing. It's not about how it actually looks in real life. And then... I didn't even... Oh, yeah. Wait. I didn't even, copy it. But it says... I only got the part that says, in this model, the strain provided by each force is the same, and the elongation of the material... So what what does it say after that? Oh, wait. Oh, no. Sorry.
Do you want me to share it? Where is
is there anything underneath this over here?
Oh, no, there's nothing underneath there.
Oh, okay. All right. So basically it's not happening independently. Deformation of the elastic component occurs over time, right? It doesn't occur instantaneously, because then it would be a vertical line.
Mm-hmm.
And or horizontal line, neither of those things really work. And then it's just an overall curve, so they're basically not responding independently, they're responding together.
Okay. Got it.
Yes. So, okay. So, yeah, that's just what it's kind of saying. It kind of also, this kind of, phenomenon also happens with, static friction, and, kinetic friction. So a lot of the times, if you're confused about proportionalities and things like that, graphs like these visually illustrate the principles quite well. So here's an example of static friction and kinetic friction. So So like remember static friction, like so do you remember those?
Like that's when it's not moving.
Yes. So yeah. So which is higher?
Static friction.
Yeah. So it's usually so okay. So basically this should kind of help you maybe connect it to something in real life. So like you're pushed, let's say it's a rock or whatever, a boulder or something that you're pushing, and at first it's not moving, so it has static friction that's resisting like you trying to move it. And so you need to apply that, like that's the applied force, and this is like the frictional force, and the frictional force increases as you apply it, right? And then it gets to a point where it starts to move. At that point, it becomes kinetic friction, and kinetic friction is always less, so then it starts to decrease. So why am I showing you this? To connect the two independent, separate parts of the graph to something in like reality, like pushing that boulder, and it finally rolling. So that's what's happening here. So basically, it seems like you elongate it like really fast until it reaches a certain like length or whatever, at which point the fluid aspect of it, the damper aspect of it kicks in, and then it starts to get elongated slowly. Right? Okay. So okay. Now, all right, let's see. Why does the Voigt model indicate an asymptotic limit? Do you remember asymptotes?
Like I know, like very basic knowledge. Like it approaches like an asymptote, stuff like that.
Mm-hmm.
Not too much.
So,
but like I know it's talking about like the shape of the graph for this one.
Yeah. So, all right, this is a good opportunity to illustrate something about proportionality. So, like, if something is like a direct proportion, like whatever, something like this, right? Then it would look like that, right? Sorry. An indirect proportion. Well, like that. Oh, sorry. If it's indirect, it would be proportional to 1 over the thing, right?
Yeah.
Now, what would that graph look like?
Like that.
Like that?
Yeah.
Now, wait. So, what if I told you that it won't look like that? So think about this over here.
1 over n, and then you're just making that n.
So the thing is that what can n not be?
What can n not be?
Yeah.
N is the
what number can it not be?
0.
Why?
So you can't have a 0 in the denominator?
Exactly. So anything that's an indirect or inverse proportion can't be like that. At 0, there will be an asymptote, and so it'll look like that.
Okay. Yeah.
It'll infinitely approach zero without ever reaching zero.
Yeah.
Okay. So, because I've seen this type of question asked a lot on the MCAT, like, they would be like, "Ooh, what does this proportionality look like?" And a lot of people would choose that, but it would be like that because of the asymptote.
Got it.
Okay, so why does the Voigt model indicate an asymptotic limit of elongation during constant stretch over time, while the Maxwell model does not? So here, right?
Yeah. Yeah, that's the asymptote.
Yeah,
So
it's
I
like a
just
little bit
didn't know
above
what
it, right?
it meant.
I'm sorry?
Yeah, I really just didn't know what it meant. Like I knew
Mhm.
where it was. I just wasn't really sure what to do with it.
Mhm.
Um,
Yeah. So it's like right there or whatever.
mhm.
And you've seen that before, like in
Yeah.
Michaelis. What's that?
Yeah, I've seen it.
Like in like a Michaelis-Menten
Yeah,
curve
no
or
offense.
something, right? Where it's like V max, I think.
Mm-hmm. Yeah.
Yep. Like this.
Yeah, I remember those.
Yeah. So same kind of deal here. Like it's not going to ever, but whatever. You get the point there. So okay, so that's basically what they're asking. So they're saying, like why in this case does it seem to go upwards towards infinity forever, whereas this in this case it starts to reach its limit.
Yeah. I don't know. I have like no idea why I picked A, but I also have no idea why it would be B.
Okay, so let's see.
And I don't even know why I got rid of D. The Voigt model counts with potential material. Yeah, that just didn't like I had no idea what it meant, so I just got rid of it.
Okay. All right, so let's see. The two component forces in parallel are dissipated. This reduces the amount of stretch possible. So when they say stretch, what do they mean?
The deformation, or no, the less like how like what variable? The X, maybe?
Yes.
Okay.
Good. Now, so okay. So that's saying that if you dissipate the two forces, that it reduces the amount of X.
Like if you dissipate the spring and the solid force? Like the six spring, the liquid stuff? The solid and liquid?
Oh, if you dissipate both, right? The solid liquid ones or fluid one, it reduces the X. I can see why you chose that because, after all, this is X.
Yeah, wait, is that not true? No, wait. If you... I actually don't really know. I thought they were proportional, though.
Yeah, they're proportional. So I guess if it dissipates the force, it should, since dissipate means get smaller, it should reduce the X as well. I could see why that would be a choice. Let's see. Well, so okay, if that was true, that could be the answer. I don't really know if they're in parallel. Wait, if they're in parallel, it's not true that the forces are dissipated though. Because then the graphs, you would see this entire thing would be tinier.
Wait, what entire thing would be tinier?
So like here. Whoops.
Like the straight line?
Oh, just the entire. So here, this and that. I wonder if I could change the opacity. Oh yeah. So. All right. So right here, right? So the elongation, right? It's still going to be basically the same essential elongation.
What?
Yeah, because this one's saying that the two component forces in parallel are dissipated, and that reduces the amount of stretch possible. But
wait, the two component forces, like I thought we were looking at like, why are you comparing those two graphs? Like, I thought we were comparing the forces, not the.
Oh well, the forces are proportional to these, right? So we can treat like over here. Sorry. Like, the force is proportional to the v, right? And sorry, proportional to elongation over here. Force proportional to x. Force proportional to v. So we can, so whatever we observe in x would be the same for the force, right?
Okay.
So if they're saying that the two component forces in parallel are dissipated, and this reduces the amount of stretch possible, and you look at like the two graphs, the only difference really is that, you know, this one it's in two different phases, and after that first phase it seems to go like infinitely. So if you look at like the two curves like this.
Yeah, I see what you're saying. I just don't really get why you're saying A is wrong.
Oh, I'm just saying that this part of it, so this thing over here, if it was right, like would answer your question, right? But this part over here saying that the two component forces in parallel are dissipated, that would mean that in parallel, since this force is dissipated, this would dissipate as well. And since this is dissipated, this would dissipate as well.
So what would the graph look like?
So, okay, so the graph would, so it would look like something like this.
Oh, so they would just be the same?
So it would be much lower, like a smaller overall, shape, since we're reducing both of the forces.
So how do we know it's not dissipated? Because they're not.
Oh, just because. So you see how. So okay, for this.
Because they're like close in line.
Like, for this first step, so it only changed. So the first step essentially is the same. It's when I say sorry, it's not the same in terms that it's not the same because it's instantaneous. Why can't I move this? Oh, sorry. So, okay, this is just instantaneous, goes up to this point. Let me just do that then. And this one can still reach that point. It's just not instantaneous.
Okay.
It's like might be hard to see like that.
Okay.
That might help.
Yeah.
So basically what this shows us is that this first part of this sentence is not true.
Okay.
Because this is saying the two component forces in parallel are dissipated, which means that this goes down and this goes down. So so it shouldn't be, the only difference between this and this is that this is occurring in one smooth movement, and after this point here, that this like level of elongation, this thing reaches like an asymptote and this thing doesn't.
Got it.
So okay, so that's the thing about A. Let me look at C and D. Let's see.
I have no idea what they're saying.
Oh, I'm just trying to now look for the viscous component. Ah, I see. That right there. So this over here, that's the viscous component.
Okay.
All right. So okay. Oh, and then I should say this is the elastic component, K.
Yep. So, yeah, there's no idea.
Okay. Then so over here they say the elastic force will Okay, so they're doing some stuff with calling things different things that could make it very confusing. So okay. Let me try to equate some of these terms. All right, so they say it's modeled as a spring. If it's solid, it's modeled as a spring, right? And then K is a stiffness or elasticity, so that's the elastic component. X, whatever, is the elongation component, or we can think of it as what? Yeah. Sorry.
Yeah, I get what all the like variables mean.
Oh yeah. Just what I noticed just now though is at the end they're saying elastic force and viscous force. So before that they basically so sorry, just because I wrote spring and damper, I put these equal signs to mean that this is the elastic force, this is the viscous force. Okay, so all right, so basically how to bring all this together. So elastic component, viscous component responds slowly over time. Why does the Voigt model Why does the Voigt model indicate an asymptotic limit of elongation during constant stretch over time, while the Maxwell model does not? The ability of the viscous component to stretch infinitely is limited by the elastic component. All right, so I can see like how it could come down to B and C. So this is saying both decrease. This is saying that if this increases, this decreases. And this is saying vice versa. This potential of material failure under extreme strain. I mean, then the thing would just break apart. All right, so you were able to cross that out. Why were you able to cross that out?
I had really no idea what it meant. And I was like running out of time, so I knew I didn't have like that much time to spend on it.
Okay, so if the material fails under extreme strain, this is what's going to happen to its graph, right? Let's say it goes up, it'll just go bam, straight down. If the material fails, it's like a rubber band that you're stretching and then it snaps.
Yeah, that makes sense.
So elongation is going to go down to 0. So basically we have our options of either both of these things going down. The viscous component and the elastic component, the viscous aspect of it, this is limited by the elastic component of this, or the elastic component is limited by the viscous component.
Yeah, I like so.
Okay, so
I get like what it's saying, but I have no idea like how to
like visualize it.
I thought that they were separate in the. I thought we said they were separate in the other ones. I have no idea what to do with that now.
Sorry, say separate in.
Actually, I have no idea, honestly.
Okay, so in order for this to be true over here, right?
Yeah.
This is saying that. So okay, well, I should have done this in the first place by just using like this as an example. So this like stretches, right? And
oh, you're looking at
sorry. So I'm stretching this. Why isn't it stretching any further?
Because it can't.
Why can't? Yeah.
You stopped stretching it?
Because what?
Because you stopped stretching it?
I mean, I could stretch it further. I can't stretch it further because this. So okay, from it being normal, as I stretch it, the elastic force of it, right? Remember how I said elastic isn't about whether it can stretch, it's about it returning back to normal after it stretches.
Mm-hmm.
So if something keeps stretching, right, it's limited by its elastic force that brings it back to normal. So I can't stretch this infinitely.
Okay.
So in this graph over here, this is showing that you can elongate or stretch something infinitely, right?
Mm-hmm.
Whereas this one over here, you cannot stretch it infinitely. And the reason for that is just the same reason why you can't stretch a rubber band infinitely. Because the elastic force that pulls it back to its original position is constantly working against the force that causes it to stretch in the first place, that causes the deformation. Right?
Got it.
So when they say the viscous force is proportional to the speed of deformation, right? So equate viscous force with deformation, which is basically causing a change in something, right?
Okay.
So that viscous component that is causing it to deform, aka stretch, that whenever you do that, the elastic component, the elastic force that pulls it back together is working against it at all times.
Okay.
Here it's like the same kind of thing over here, where I draw. Do you see this over here?
Mm-hmm.
Yes. So the blue arrows think of that as the viscous force, aka deformation, aka moving it away from what it's normally supposed to be. And then the green arrows are the elastic force that pulls it back to what it wants to be normally. So basically what's happening is that the elastic component prevents it from deforming infinitely. And the confusion in this lies in just the fact that they're using words for, like, so many different words for all these things. So I'm just going to write, like, viscous component equals deformation equals stretch versus elastic component, which equals, I don't know, reformation equals I don't know, whatever's the opposite of stretch, like return to, or like de-stretch, or no, relax, maybe. Yeah, sorry. That was so this was a very overly abstract passage that we can just boil down to just how any type of elastic material behaves. So, like, this, like, picture and that picture aren't really going to, I guess, like, help you as much.
Okay.
I mean, they can help you because this is just saying that they're separate, and this is saying that they're working in tune with one another, because they are working in tune with one another. As this goes up, this goes down.
Yeah.
I hope that was yeah, I hope that sort of made sense. Like, just think of it like just think of like a rubber band. You're pulling against it, and the elasticity of the rubber band itself fights that to bring it back.
Mm-hmm.
And in the Voigt model, where it's parallel, right? Like, when the thing moves like that way or whatever, they're both working. They both work. One can't work without the other. That's the main takeaway.
Got it.
Okay. Yeah, I don't think you'll see a passage like that on the MCAT.
Yeah, because I don't really get any of the questions on this passage, honestly, but actually, I don't really want to do this passage anymore.
You could share your screen. I'll just take a look at the questions and see if they're insurmountable.
Fine. Wait. There's this one. There's this graph one. And then where does it go to? 9. Then this one too.
All right, let me see that first one for a sec. If it's too much, we'll skip it. Let's see. Constant force, Maxwell model, which is the series thing. What would be the initial elongation value at t is equal to 0? Constant force is applied. Okay. Okay, so at t is equal to 0, right? It's just that the elastic whatever component thing, right?
Mm-hmm.
Like, that's what happens first. That's why the k comes first. So in this one, they're just asking. So that means that we're going to use Hooke's law, because that's the one that's associated with elastic force. And since they're asking elongation value, we're going to solve for x. So you just take Hooke's law, and then you rearrange it to solve for x. So you divide, k on both sides.
Okay.
All right, now this one, so this is exactly like the Voigt model, except there's an additional spring there that is in series with the the two things that are in parallel. So this is going to basically give you so it's going to start off with that kind of curve thing, but that additional spring that's in series with, because it's like the first two things that are in parallel, you can combine, and then it's in series with that k that comes after. So what you're going to get is something that is going to be a mixture of what you see in the Voigt model curve and the Maxwell model curve. So you're going to see essentially like something like a vertical line, and then like a curve kind of thing. So Okay, so yeah, your choice is very good.
Yeah, I don't like fully get this one, but I think this one's probably like
So
um
so the fact that it's parallel means that there will be an asymptote, right? And then the fact that it then later becomes series means that there will be a vertical line.
wait, where is it this is the parallel, this K with this K?
That's it series. So first the K and the N, those are in parallel,
Okay.
right? Like if you look at that Voigt model, you see how they're in parallel? Like circuits kind of.
Yeah.
So okay, if things are in parallel, what you're going to get is an asymptote. Because the K and the N are working against each other. Now, if it's in series, what you're going to get is a vertical line. And that's just because if it's in series, instead of them working at the same time, it's going to be K working first and then N. So, since this is a combination of parallel, the K and the N in parallel, we're going to see something with like an asymptote. And since the result of that is in series with that K that comes after, you're going to see a vertical line. So yeah, you chose a good one. Because you got the curve, which is like the
Yeah,
thing in
I mean,
parallel.
I'm pretty sure I just completely guessed on this, so
Mhm.
I don't really think I had like a reason to chose that. But I
Okay. All right. How about this? You can send me these questions, and then I'll write about them and explain them in the OneNote.
Okay, yeah, because I don't have. This one I ran out of time, but I like really don't get any of these.
Okay.
Um,
Yeah, we can.
but
I can explain those in like a OneNote for you, for like time's sake.
the 28. Oh wait, no, I got this. Hold on.
I'll be right back. I'm just gonna get some water. Okay.
Okay. Oh, stop sharing. This was the other chem passage that I like really wasn't too sure on. Yeah.
Yeah, these Kaplan passages are crazy. All right, let's see. A heater is used to calibrate a constant volume calorimeter. Okay, that's figure 1. Measures the energy content of a substance. The bomb, which holds, okay. Okay. So, like, the takeaway there is that you can measure the energy by checking the temperature of the water, like how it changes. Like a combustion reaction essentially happens inside of it.
Wait,
Mhm.
I took my notes. I just like looked at this passage probably a couple hours ago. Oh, found it. Okay. All right. What did you say?
Um, uh, oh yeah. So they're saying a heater is used to calibrate a constant volume calorimeter. So I would look at where it says constant volume calorimeter in the second paragraph. And so, I mean, you've heard of like, I guess, calorimeters before,
Yeah.
right? So basically, they just like cause it to combust, which produces heat. And in this type of calorimeter, constant volume one, they just measure the change in temperature of the water that surrounds it, and that's how they ascertain the energy content of whatever that they combust inside of it.
Okay, yeah. I just checked so this is this one and the other one were the only ones that I like. Well, these two are the ones that I ran out of time on, but then when I looked this section over, these two passages are the only two that I like couldn't figure out on my own.
Mm-hmm.
Like all the other ones I was able to kind of get with like time or just see what I did wrong, but these ones I like literally have no idea what I did.
Okay. Do you want me to go over like the passage kind of? Or
maybe like I just went over this passage is like a little easier for me to kind of digest because it's literally like just explaining what this constant volume one does. The other one I couldn't really like digest. So this one I get, but then like when I tried to do the question by myself, I couldn't.
Mm-hmm.
But like I was able to kind of like break the passage down a little more.
Okay. Let's see. A heater is used to calibrate a constant volume calorimeter. So that's probably used to, get some baseline for the water temperature. So when you actually use it, you can see, like, by how much, it changed. Okay.
Yeah, wait, actually, can we go over like notes to take on this passage? Because I went over it, but my notes are going to be like way too long for me to actually take the test.
Here. All right.
Oh, do you want me to stop sharing my screen?
Can you see mine?
No.
Okay. Yeah. I don't know why. Like it says multiple people can share, but it never works.
Yeah, I can't see.
Okay.
Yeah. Is like that important, so I didn't really take much. Like it's just, I don't know. Like I figured that that's just telling us like you can measure the amount of energy by combustion.
Yeah.
But the second paragraph, I was like, whoa.
This over here?
Yeah, then like after I wasn't sure how to just like write notes and see.
Oh, okay. So okay. So basically what's happening here is so like, let's say you wanted to figure out the energy content in like a candy bar or something. Energy, we're going to just basically blow it up essentially, using a combustion reaction, which is yeah. Yeah, and so since it's at a constant volume, when we combust it, right, which is going to basically create like lots of like carbon dioxide and like water vapor, aka lots of gases, which are going to increase the pressure and, cause the volume to expand. Since it's constant volume, we don't have to worry about that pressure aspect of it. So we can just concentrate on the temperature change, like the heat. All right. So that's just so that's how that basically works. And then let's see. So before we can actually calculate that, we have to calibrate it, right? We need to see the heat capacity of the bomb. And then they say the heat capacity of the bomb is the product of the specific heat and the mass of the bomb. So I would write, heat capacity bomb equal to C, which is whatever specific heat. Do you remember specific heat? Yeah.
It's given, right? Like a constant or no?
Yeah.
Different materials, it's constant.
Yeah, for this one.
Yeah, QMK. Yeah.
Yeah. So if we're using water, we'd use the heat capacity of water. And the heat capacity essentially, specific heat. Well, all right, whatever. Specific heat is essentially how much energy, aka heat, something can take, or a mass of something can take, before it rises in temperature by 1 degree.
Okay.
Yeah. So the heat capacity of the bomb, they're saying, is the product of the specific heat and the mass of the bomb.
Okay.
So here in blue, yeah.
Yeah.
So
actually, getting that from the heat capacity is that times the mass.
Mm-hmm.
Why do I have? Where are you getting that from?
Third paragraph, last sentence.
Heat specific heat times the mass of the bomb. Oh. Okay.
Yeah. So okay. So yeah. So they need to basically figure out the heat capacity first before they can actually determine or get any valid readings or accurate readings.
Okay.
So
Settings for no.
so
Yeah, so that's I guess also then if you look at the question, I was like, well, actually no, I guess we can go finish the passages before because that might be why.
So imagine a container within a container. All right, this is the bomb, and this is water. Now we know the heat capacity of water, we know the specific heat of water. We know whatever mass of it's there, and therefore, we can, from seeing the change in temperature of the water, we can determine the heat that's produced, right?
Yeah.
All right. Now, the bomb calorimeter thing, the constant value volume calorimeter, is within this container, submerged in water. So if something goes boom in there, it's going to shoot out some energy, like heat, right, against the walls of this bomb, constant this container over here. Here, I'll draw it like on a side view. Like that.
Okay.
So, inside of here, decombustion reaction happens. It gives off heat. And this, the bomb, whatever, like, let's just, this, like, it's most likely made out of some type of metal or something, right?
Yeah.
So that metal will absorb some amount of heat to produce an increase in temperature of this material, which will then translate into heating the water around it, which will increase, which will
So then
Mm-hmm.
it says something about how they're in, oh wait, never mind, that's a question. Actually, yeah, so you're saying like that absorbs the heat and then the heat goes to the water, so it heats up the water.
Yeah,
then...
it could be the other way around, I think. But either way, the idea is that... Sorry, what were you saying?
Trying to find it. I don't know. I thought I said something in the passage, but maybe just in the question about how they're in thermal equilibrium, and I thought that, I don't know. I thought that was like why I didn't really know what to do with that actually.
Let me see. Where are you saying that?
I thought it was in the passage, but now I can't find it. It says it in the question, but yeah, I guess it's not in the passage. Never mind.
Oh, I see it. It's in the question. Note at the end.
Yeah, I like didn't really know what to do with that, but I thought it was in the question, so I thought that that's why you can use the temperature of water. So I guess it's unrelated.
Oh no. So that's just saying that the bomb and the water surrounding it remain in thermal equilibrium. That means that no heat escapes. Like all the heat. So basically, you're making an explosion inside of some container that produces heat against the walls of the container, and all of that heat is going to be transferred into that water surrounding it. None of that water is lost, so that's what's meant by them being in thermal equilibrium.
Okay, so got it. Okay.
Yes. So the entire idea here is that since we're, in order for us to get an accurate reading using just the change in temperature of water, we need to know like pretty much exactly like how much of this heat, like how much of it changes as it moves from the as the heat moves from the bomb part to the water part at this interface.
Oh, are you on the question now?
I actually haven't looked at it yet, but
Okay, because that's like kind of what it's asking.
oh yeah,
That's why.
yeah. So like the entire idea. So like if you've ever wondered like what's the point of this entire thing,
Yeah.
it's like this is heat capacity, and this is the mass. This is the specific heat, and usually in this the cases would involve water, and this is the change in temperature. So imagine like this. So um, let's say whatever you shoot heat energy into like 1 gram of water, right? And I think the specific heat of water was like 4.18 or something like that. Yes, 4.18. So so this water guy will absorb 4.18 joules of heat before it goes from, I don't know, like whatever, like 1 degree or whatever, 10 degrees Celsius to 11 degrees Celsius.
Okay.
Sorry. Like right there. So water essentially, so you're shooting heat in some mass, let's say 1 gram of water, and since water has a specific heat of 4.18 joules, which by the way is really high, it absorbs that much heat energy before it goes up in temperature.
Okay.
So that's why water usually doesn't change temperature that much. Like if you just have it like lying around in the house or outside, or if it's really hot, it's usually like pretty like the temperature is usually like not going to be changing by wildly, crazy amounts. All right? So that, think of that as like heat capacity. How much this can take, how much heat it can take before it goes up in temperature. All right. Now, since we're not just using water,
Yeah, that's for C, right? That's what we did before. That's the heat capacity.
what are you saying? Oh, so this is for water. Now,
Yeah, no.
yeah.
You're saying that's like the C, like the how much heat it can take is the heat capacity, not the Q, right?
When you say C, you mean
It is like C is like the variable.
like this?
Yeah.
Oh, sorry. No, little c is specific.
Oh, the specific heat, and then Q is the heat capacity.
Yeah.
Oh. So Q is how much heat it can take. Oh no.
Mm-hmm.
Is Q how much heat it can take for it to raise 1 degree?
Oh, so the specific heat, that is how much heat it can take, how much heat a specific mass of it can take before it goes up by 1 degree.
And then, so how is that different than Q?
Q is the overall heat energy that it can take, that it can hold. So like so 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 if you want, so like if you wanted to see how much heat, like if you wanted to see the capacity of heat that a gram of water can hold, right?
Mm.
It's, you're going to be using, the mass, which is a gram, change in temperature, which will be whatever, 1 degree, and then the specific heat. So the heat capacity, right? So the 4.18 joules, here, I'm going to do this. Specific heat for water is 4.18 joules per gram times Celsius?
I think it's Kelvin, but I could be wrong.
Yeah, it could be either Kelvin or Celsius, because if it's delta T, like 25 like Celsius minus 20 Celsius, 298.
Yeah, we can just call it Celsius.
Okay. Because it's delta, so you can do it either or. But yeah, let's just whatever. We'll do Kelvin. So specific heat is for water is 4.18 joules per gram, times whatever Kelvin, Celsius, whatever, right? Now let's say that for M is equal to 1 gram, delta T 1 Kelvin, right? Then the heat capacity of water, right, would be 1 gram times 4.18 joules over grams times Kelvin times 1 Kelvin, giving you 4.18 joules.
Wait, I'm just confused. What is this for? Like,
Oh, so
what are you showing me with that?
okay, so this is just so this is just to explain what heat capacity is.
Okay.
And for water, since we know the specific heat of water, we can figure all of this stuff out. But since the combustion reaction happens first inside of that in the bomb, we need to know the heat capacity of the bomb.
Okay.
Because like if the walls of the bomb or whatever, that container has whatever a specific heat of like 1,000,000 joules per gram times Kelvin, then that means that a 1 degree change that we'll measure in the water is not going to be what we think it is. Because it depends on whatever it is for that bomb.
Okay.
Like, we know everything about water, we just need to calibrate it to make sure that we know the things about the bomb, right? Because if the walls of the bomb can absorb or has the heat capacity of 1,000,000,000 joules, then if we tried to figure out the number of calories in something that produces like 1,000,000,000 joules, we're not going to get an accurate measurement. We're just going to get a 1 degree increase in water, because the bomb, if its heat capacity is super high, it's just going to absorb it all.
Got it.
Okay. So that's why they're saying before the heat or energy produced by the reaction can be calculated, we need to calibrate it. That means we need to determine the heat capacity of the bomb.
Okay. So.
Like, almost like, think of it like it's like outside there, it's a specific temperature. Inside, it's a different temperature, right?
Yeah, I'm getting it confused. I thought.
Yeah.
I don't really know yet. Like, I thought I kind of got this passage, but now I'm like really confused on it.
Okay.
I don't even know like where I'm confused, but. Like, yeah, I have no idea what's going on anymore.
Okay, let's see. Alright, you know how, have you ever seen like like for like a drink, like a insulating cup being put over it, like a sleeve, right?
Oh.
I mean, I don't have it, but like, let's say, like, you know, like a sleeve over it.
Mm-hmm.
So that sleeve, right, is going to absorb some of that like energy, right? Like for coffee, right? Coffee is hot, right? And then they put that like sleeve thing over it. So what you feel isn't as hot. Now, that's because the heat that's produced by the coffee, right, is absorbed by the material of that sleeve.
Okay.
So that means that the sleeve has a heat capacity. Whenever you see heat capacity, think of it as like how much heat it can carry without you noticing.
Without what?
Oh, without you noticing.
Okay.
So, if you had a coffee cup, right? That has really hot coffee in it, and you have like, you know, that those sleeves, those like cardboard sleeves that they put over it.
Yeah.
Then the measurement that you have, like, or how it feels in your hand, is going to be like a lot less hot. Like, it's going to be a lower temperature than the thing that's inside of it, right?
Yeah.
So that means that sleeve has a heat capacity that is absorbing the heat produced by that coffee. So if you were to like take a reading of the temperature of the coffee, you cannot do it by measuring from the outside, because the heat produced by that coffee is absorbed by that sleeve.
Okay.
So now think of it just like that. Think of this like bomb aspect as the actual coffee, right? Producing heat, right?
Mm-hmm.
And you know, the like material that it's made out of, think of that as the sleeve.
Okay.
And that sleeve has a heat capacity, so it absorbs some of that heat. So what you get out isn't going to be equal to the actual heat or temperature of that coffee inside of it.
Okay.
So how's that?
Yeah. Okay, got it.
So
Okay.
So in this case, in
So
order, yeah.
both.
What's
Is
up?
what you're saying? So you're saying you have to measure them both.
Sorry?
You're saying you have to measure like both the heat in here and then the heat of the outside thing.
Yeah, because we can't get an accurate, because if the reading that they get is just from the change in temperature of the water.
Yeah. Okay, that makes sense.
But if the bomb aspect of it is absorbing so much of that heat, it's not enough of it is going to touch the water. So that water isn't going to rise, the temperature of the water isn't going to change accurately. It's going
Right.
to be like less because it absorbs it, right?
Yeah, that makes sense.
Yeah, so in order for us to get an accurate reading, we need to figure out the heat capacity of the bomb aspect of it, aka the heat capacity of the sleeve of the thing around the coffee.
Okay.
All right. So does that make sense, like, conceptually?
Yeah.
Okay.
one, we can look at the question. A heater is used to calibrate a constant volume parameter. After operating a heater inside the bomb, which of the following physical quantities must be determined? That's why it's like kind of similar to what we're explaining, but
All right, so
Power.
heat capacity, what unit would that have?
heat capacity is that the Q. So, joules.
Correct. Power, what unit would that
Power
have?
is 1 time, right?
Good.
Work over time. Work is Newton per second. Am I wrong? Like, work is Newtons and time would be seconds, so is power Newtons per second?
Work is equivalent to what?
Right?
Wait, sorry?
Work is joules.
Yes.
Okay.
Which is newtons times meters, but yeah.
Yeah, Newton meters per second.
Mm-hmm. So power is just joules over second, right?
Yeah.
So how do you get from power to, like, energy or work?
From power to work or power to heat? What are we doing?
Oh, so energy and work are the same.
Oh, we want power times time.
Yeah. Good.
Joules.
Mm-hmm.
So we want power of the heater times the time. And the change in temperature of the water?
Yep. Because think about it. We have all this stuff. If we get delta T, right? And if we get power of the heater and total time the heater was operated, right? Multiply the power and that total time, you'll get this. You'll get the Q. You'll get the overall heat capacity of the bomb, right?
Mm-hmm. Wait, I actually kind of get it with what we just did.
Mm-hmm.
I wouldn't have like known to do that. Like, I didn't think it was temperature of the water only, but how can I like rule that out?
Because we don't know anything about the heat capacity of the bomb, right? That's the thing that we need to determine in order to calibrate it, right? So this is like how, yeah, like it says a heater is used to calibrate. When I see calibrate, I go to the passage, third paragraph says calibrate the calorimeter, right? So what does that mean? It means you must determine the heat capacity of the bomb.
Wait, so the heat capacity, we want to determine Q, which in order to determine Q, we need.
You got it before.
Yeah, I got it with the units, but I just don't know how I would like know conceptually power comes in. Like their explanation for it was super weird. It didn't really help me.
What was their explanation?
Like we did heat capacity equals Q over delta T. I can share it with you if you want. But basically like short version is they said heat capacity equals Q over delta T, which I'm confused about because isn't Q heat capacity?
You said heat capacity Q over delta T?
Yeah, and isn't Q the heat capacity?
Wait a sec. Oh, okay. I see. All right. I think I was wrong about this heat capacity part for water over here. Because now this heat capacity is just what's missing here, like compared to this.
What? So is Q not heat capacity, is what you're saying?
Yeah, my bad. Q is just heat. Just straight up heat energy. So here. So
like, is everything about Q then, it's not like the overall heat energy, or anything?
Here. Let me clarify here. So Q is heat, but let's say you didn't know that, right? If they said the heat capacity of the bomb, let's say we don't know what that is.
I knew Q was heat, but that's why I was confused before.
Oh yeah, that was my bad when I put heat capacity for this one. But if you just look at heat capacity of bomb, right? It's equal to the mass of the bomb times the specific heat, right?
Yeah.
So if Q is heat, and that's equal to the mass times the specific heat times delta T. Here, check this out. So heat capacity, right? It's equal to, like from here, heat capacity is a product of the specific heat, which is C, and the mass, right?
Yeah, that's what I have in, like,
Mm-hmm.
but then what is heat capacity? Like,
All right. So here, now, if this is heat right here, right? Q is equal to M, like mass specific heat times delta T. And heat capacity is equal to, maybe if I put it in the same order, like you see how there's MC here and C and M here?
Yeah.
So the only difference between this and this is that this has a delta T here. So in order for these to be equal, you would have to, you'd have to divide both sides by delta T to get Q over delta T is equal to mass times the heat capacity. I'm sorry. Mass times the specific heat, which is exactly what this is, it right? Heat capacity.
We don't have to do this one now.
Oh, okay.
If you want.
Just see if this makes sense right here. If the heat capacity of the bomb is the product of the specific heat times the mass of the bomb, right? And if heat is equal to the product of the mass times the specific heat times delta T, in order for these guys to be the same, right, I could divide delta T on both sides. So then I would get Q over delta T is equal to the mass, the product of the mass and the specific heat, right?
Mm-hmm.
Which is exactly what this is, right? Heat capacity of the bomb.
Mm-hmm. Got it. Yeah. I wanted to do like cars, but I don't know. I don't think I want to do that anymore.
We could do cars if you want.
It's gonna be a long one, that one. So I think that's probably it for today then.
Okay.
Yeah.
Okay.
Yeah. Because that was like really long.
All right.
And,
You had a long day.
yeah. I'll go through these and I'm confused on these. But yeah. All right. I'll just try and look them over tomorrow.
All right. I'm gonna in your OneNote. I'm going to like I'll write down some stuff. Hopefully, that'll make it more clear.
Okay.
Okay.
Yep.
All right. All right. Yeah. Don't worry. It'll be okay.
Okay.
All right.
All right.
All right. Take care.